Thanks, Brian. So today we're going to talk about some high-performance networking using Kubevirt. My name is Doug Smith, as Brian introduced. I'm from the Red Hat office of the CTO. In my particular team, we work on networking, and we also work with strategic partners of Red Hat, specifically looking at NFV situations. And I'm joined today by Abdul.
So I'm Abdul Halim, and I work in Intel. I work as a cloud software engineer in a network platform working group, and I'm focused on enabling some of the NFV use cases in Kubernetes.
Today we kind of have 3 parts here for you. We're going to introduce Kubevirt, a little bit of the how and why behind Kubevirt, and we're going to dig into some of the details behind SR-IOV and the SR-IOV device plugin, which is one of the ways that we enable some high-performance networking use cases with Kubevirt. And then we're going to end with a demo, and that demo, it's a pre-recorded demo. However, we also have a kind of do-it-yourself workshop that we have available online so that you can go home and try out all the pieces yourself step by step. So let's just talk about Kubevirt a little bit. And really, Kubevirt is a way to take your virtual machine workloads and run them under Kubernetes. So this is something that you can do in order to prevent yourself from having to, say, maintain 2 separate platforms. You're seeing a lot of benefits out of using Kubernetes for DevOps, and you might have workloads that just aren't containerized yet, right? So we might ask the question, well, can I just containerize everything? And the thing is, sometimes that's just not really a possibility. Sometimes maybe your vendor has shipped you software that's already a virtual machine, and now you've got to run it. And do you really want to have another platform when you've got a lot of forward progress here in order to run your containerized workloads? Maybe you need kernel customizations, and as you know, your containers are utilizing your host kernel. And maybe you just like having some pets. Maybe they're part of the family and you just want to keep them around. So here's the thing. Now we've got this like crazy world here where we've got containers and VMs side by side, right? And we're going to be able to take those and build them, deploy them, maintain them all in the same environment. We're going to be able to keep our same workflow that we know and love under Kubernetes, and we're going to be able to migrate these workloads to potentially be containers in the future if you want, or don't. Just keep them as a virtual machine. So how do we actually do this? And the thing is, it's really not that complex. It's just an addition that you use with Kubernetes. You're just going to use the same kind of workflows. You're going to create images that you're going to store in a registry that are going to be your container images that are also you're going to spin up your virtual machines from. You're going to create YAML pod specs, and you're going to deploy those, and it's going to look almost just like you would for any other workload that you have running in Kube. And Kubevirt really does try to follow the best practices that are already laid forward in Kubernetes for you. So it's not like you're going to have a huge diversion from everything else that you have going on. So let's take a look at what a Kubevirt virtual machine looks like. And really, you've got your node, you've got your container runtime running on it, and then you're going to have a daemon set that's got your virt handler, and then that's going to spin up a pod that is your VM. And so a pod, of course, is kind of a logically grouped set of containers. You've got kind of a sandbox namespace that these containers live in. And you're going to have one that's your launcher. You're going to have an instance of libvirt itself. And then you're going to have your container running therein. So it's not really that complex. And you can just use kubectl describe and see, boom, boom, boom. There's all your pieces that you've got running. So let's take a little bit of a look at our networking. So we've got here our custom kind of YAML on the left and a little diagram showing that we'd have our VM running in a pod and it's going to have an IP address connected to the default network. So we assign an IP address to it, right? And it connects to our default network. And when I say default network, I mean our network that we get our pod-to-pod connectivity from. So this is something that we're always going to want to have. You're going to have other services that you're going to consume on your control plane, be it maybe you're going to get metadata from a database or something like that. You're going to want to connect to the rest of your cluster as you normally would. So you might assign that with DHCP. And you've got here on the left this kind of definition of your interfaces. So you've got your default interface and your default network, and those are connected. And then what we're going to do is we're going to plumb another interface into the virtual machine, right? And into the pod by definition, since we're running in Kubernetes. And so we have this other network. So this is going to be your data plane. So this is where you're going to have your high performance needs. There's something that you're going to do on this, this network. So in our demo in this case, it's a voice over IP application. Yours could be anything that your heart desires. So we have on the left here our YAML that defines this secondary other interface and this other network. And that's really all that you have to do in order to enable this. Kubevirt is managed by an operator, so everything in order to do this is already packaged with you and already configured. All that you've got to do once you launch this operator is just specify these additional parameters and you're off to the races. It's really not difficult at all. So something that I'm really fond of with Kubevirt is how Kubevirt is able to leverage technologies that are across the open source ecosystem. It's not coming in and saying, hey, we're going to invent everything new from the ground up. This is all technology that you know and love if you're already a user of virtual machines. And then for the stuff that's up and coming in Kubernetes, Kubevirt has focused on taking components that have had a healthy life upstream. And these guys have been very involved in what's been going on. And so, for example, it's using operator framework. It's using a number of CNI plugins in order to plumb these additional interfaces that are maintained by the CNI maintainers themselves. They're the official plugins. And it's also using the SR-IOV device plugin from upstream. So one of the particular standards that Kubevirt implements is something that was created by the Network Plumbing Working Group, which is a group that was formed at KubeCon 2017 in Austin. And is a number of people that were interested in looking at the kind of multi-networking problem in Kubernetes to answer the question, hey, how do I attach multiple networks to a pod? So the Network Plumbing Working Group came together and they created a de facto standard for a CRD, custom resource definition in Kubernetes that's called the network attachment definition. And it essentially specifies how do I express my intent attach an additional interface to a pod. And Kubevirt uses this in order to accomplish what we showed in those previous diagrams with attaching that interface. Specifically, the technology that's used to execute that custom resource is Maltese CNI, of which I am a maintainer. And Maltese is a meta plugin. So it's a CNI plugin that's able to call other CNI plugins. So essentially, it's called, you have what other additional configurations that you have that say call this other CNI plugin, and it uses that in order to attach these additional networks to the pod. So let's talk about device plugins for just a moment. So in order to use SR-IOV interfaces, we use an SR-IOV device plugin. Device plugins give the Kubernetes schedule awareness of physical resources that have been utilized on a particular node. So in the case of SR-IOV, we have physical functions, and then we have virtual functions. And when you use a virtual function, this is a resource that can be exhausted on a particular host. So you go and create your VM, it's in a pod, it uses an SR-IOV interface, and the device plugin lets the Kubernetes scheduler know, hey, this resource has been used up. So that way, this works at scale. So you schedule workloads on a node until it's full, then the Kubernetes scheduler is told by the device plugin, hey, this node, it's full, don't schedule any more pods here. And so previously, there's been like a SR-IOV CNI plugin that's still used, and that works, but if you were to go and spin up a ton of pods without the device plugin, the scheduler doesn't know where these workloads belong. So let's take a look at the SR-IOV device plugin.
Thanks, sir. Thanks. So in this section, I'm going to talk about that why do we care about SR-IOV networking, and then we'll look into the evolution of SR-IOV networking support in Kubernetes, and we'll also look into how the overall system works in orchestration of the SR-IOV resources in Kubernetes. So here we see in the traditional virtualized environment, we see that each VM gets a virtual interface from the hypervisor by some kind of mechanism of virtual switches or Linux bridge. So this virtual switch or Linux bridge introduce some additional overhead, which maybe affect your performance workload. So it can introduce more latency and less throughput. So this may be not sufficient for the many use cases. For example, high performance NFV use cases, we need really fast data plane. So here we see, so ideally we'd like to have, if you'd like to remove this overhead, we'd like to have a direct NIC assignment to the each VM. But problem with that is we have limited number of I/O port in a system, so that's the problem with the scalability. So here is where the SR-IOV, they come here to help. So we can see that in SR-IOV, we have a way of one device appear to be multiple PCIe device. So each of these devices can be discovered and configured independently. So each VM now can get a VF directly. So SR-IOV introduced this concept of physical function and virtual function. Physical functions are like an ordinary PCIe device. They have full configuration resources, and they can appear as normal PCIe devices. On the other hand, the VFs are the lightweight PCIe function device. So here, VF can do the DMA directly without any interference, but for any configuration, it needs to be communicated through the PF itself. So now we'll see, okay, how we enable this SR-IOV SR-IOV networking in Kubernetes. So initial work was done by Tencent. They created this SR-IOV CNI plugin to enable SR-IOV networking in Kubernetes. So when you started looking into that, we discovered there were some shortcomings that the CNI plugin didn't handle properly the device accounting that which BFs are free or which ones are not free. So we started extending this plugin and added this BF management capabilities. So now CNI plugin can allocate a BF which one is free, which one is not in use, and the one is used. The one is not free, you don't touch that one. So we also wanted to have this BF to be used in the DPDK application. So we also added capabilities so that BF can be attached to a DPDK capable driver. But problem with that was that we were replacing the existing default ETH0 interface in a pod. We wanted to maintain the Kubernetes control plane traffic to the ETH0 interface, and we want to add additional data plane through the SR-IOV network. So for that, Maltese there to help. So we started working on the Maltese. Maltese was a way to introduce an additional interface in there. So now we can add the data plane network through a SR-IOV CNI plugin. So by looking into this picture, you may think, okay, that's SR-IOV CNI plugin is enough to solve your SR-IOV networking problem in Kubernetes. But we hit into some limitation here when you want to see. So there's, as Doug already touched into that scheduler is not aware of these resources. So CNI plugin is not a place that it can communicate to the Kubernetes API. We also wanted to, if we want to ensure the really high performance capabilities, we want to ensure that these BFs are coming from the same NUMA socket of your CPU and memories. So this is also cannot be addressed in the CNI plugin itself. Then if we want to add this BF in a, using as a user space driver, where we couldn't do this CPU, C group isolation through the CNI plugin as well. So for that, we started looking at the possible solutions. So device plugin was the perfect fit for all of these problems. Just the NUMA alignment is still not possible because we are still working on with the Kubernetes upstream to get our topology manager KP to be merged. So once that goes in there, we can address the NUMA alignment as well. So this is just a brief overview of how our device plugin works in Kubernetes. So device plugin is a standalone binaries. It implements the device plugin API, and the responsibility of this is to discover the devices, and then kubelet can make a request for a device allocation for a workload, and then device plugin send required configuration, runtime configuration for those devices. So this is how the overall solution fits now. So we have the device plugin responsible to discovering the SR-IOV network resource in the host. Then through the Maltese, we get the Maltese delegates this SR-IOV CNI plugin to enable this BF as additional interface as a net zero. So here is the pod spec. So we have the device plugin that discovers and then updates the node status as a, you can see the highlighted purple writing there that this resource are discovered for this node, and this can update it to the Kubernetes API. Then we create the net attachment CRD for Maltese to say that we are going to use this BF using this resource, and that's going to use the SR-IOV CNI plugin. Then in the pod spec, we have this network CRD annotation in there, and then we also add this resource request that we're going to use one BF from this SR-IOV resource pool. So this is the overall flow. So you have a pod coming in with the SR-IOV network resource requirement in the pod spec, and then kubelet does once the pod is scheduled to this node, kubelet does the resource allocation through the device plugin, and then Maltese during the network creation, Maltese attach those BF into the pod. So here are some links for the reference. Anyone would like to contribute to this project? This is a joint collaboration between Red Hat and many others, and we are working on this to improve the features in there. And there are some additional documentation how the design proposal evolved over time. And we also have the Slack channels that we regularly talk and communicate with people and hear the use cases. So we also have some demo going on in Intel booth, so you can see the live demo how the whole orchestration works in the SR-IOV device plugin in Kubernetes. And we also have some benchmarking results. Anyone interested to see that? So you're welcome to come along. So with that, I'll hand over to Doug to show you the rest of the stuff.
Thanks, Abdul. So just quickly, I just wanted to take a look at some of the roadmap for SR-IOV. And some of the things that to me are the most important things are functionality that we need to be able to push all of the performance that we can out of here. So you can bring up all these tools, you can get all of it working, but we still need some forward progress on CPU management and NUMA alignment. So with those two pieces in place, we're going to be able to crunch all of the performance that we can out of these. With some of the newer hardware, you might be able to get pretty close, but you're going to be able to really push out all of that performance with all of your hardware if you've got these in place. So we're working towards that. So let's take a look at a demo. Let me get this up here. All right, so quick preamble here is that what we're going to do is we're going to spin up some virtual machines with Kubevirt, and then what I'm going to do is I'm going to spin up 2 virtual machines that have voice over IP workloads on them, and we're going to put traffic from those over our data plane onto SR-IOV. I chose voice over IP specifically because it's a kind of workload that doesn't look like your everyday web scale workload in Kubernetes. So the web scale guys, they always have it easy. You can use the single interface. You can just use TCP, HTTPS type traffic. But in the networking world, often we have the kind of traffic that just doesn't fit that mold quite as well. So I kind of wanted to highlight that. So think about the VoIP workload in terms of what you might actually put on there. So I have a background in telephony, so this is, of course, interesting to me, but you might substitute it with just about anything that's there. So let's take a look at this particular demo. So what I'm showing here is that we've got this 3-node cluster. Only one of these nodes has one of these nodes has the SR-IOV devices here. So it's the one with the non-uniform name. And so I'm just running LSPCI, and I'm just showing that we've got this 32 different VFs available here. So what we're going to do is we're going to just spin up a Ceros VM. So that's like kind of a classic type of virtual machine workload for a test scenario. So kind of just 2 quick steps here. There may even be more efficient ways to do this, but just a kubectl create from a YAML spec. We'll look at the details of one for SR-IOV in a second, and then I just use Kubevirt's virtctl command to start this VM. Then I just watch it come up. It doesn't take long at all. And then what I'm going to do is I'm going to console into this VM. And there we go, just like you're at any VM console. And I'm going to run IPA here. And something that I just wanted to point out in sort of your vanilla virtual machine is when I run IPA, I've just got a loopback, always got a loopback, and you've got your ETH0 here. And in this case, this is kind of your like typical flannel address that you would have assigned to it. So that's what it looks like to just spin up any VM. Now let's take a look at the specification for a for a workload that is going to have SR-IOV connected to it. So here we see in the spec, we've got this special kind virtual machine instance. That's how we specify that this is going to be handled by Kubevirt. And we've got a number of things here that are relevant, one of which is your image here. So just like any kind of spec for a workload in Kubernetes, you're going to say, hey, this is the image I'm using. But in this particular case, it's kind of our disk image for the VM, right? So this one is a Fedora VM. And we're going to specify here in the networks that we're using Maltese for our additional network. So we're still connected to the default network. But then we are going to specify that we have this network name, which is SR-IOV net. And this maps to a configuration that we have stored. So let's take a look at these particular network attachment definitions. So here I'm saying, let's get these custom resources that we have for our network attachments, which are essentially going to be our configurations that we have for each of our additional interfaces. And we have one named SR-IOV net, just as we had specified in the spec for Kubevirt. And let's describe this here quick. And we're going to see that there is, it's a kind network attachment definition. And we have a config here. And this is a CNI configuration that's packaged as part of the content of this custom resource. The things, granted, it's all condensed JSON, which isn't always the nicest to read, but I think the stuff that's the most important for now is that we've got a type of SR-IOV. That means that's the binary that CNI is going to call on disk. And then we have the name SR-IOV net. So this maps from what we had in our YAML spec, what we have here as our name SR-IOV net here, and we see that it's there. So that's our mapping of which configuration do we want SR-IOV net. Oops. All right, next what we're going to do is we're going to take a look at some running VMs here. We've got two VMs running where these instances are virtual machine instance SR-IOV and virtual machine interface instance SR-IOV2. So let's take a look at the pods that we have running, and we can see that there are those VMs running as pods. You can check them out with kubectl just like any other pod. And I'm going to go ahead and describe this node so that we can take a look at the allocated resources on this particular node. So on this node, we can see that we've got this type of resource that's intel.com/SR-IOV, and we have two requests for that type of resource. So that's our request from our VMs that we have running for those SR-IOV interfaces. So this is how the device plugin is keeping track of these particular resources that it has going. So let's, what we're going to do is use kubectl to describe the node and look at our allocatable resources, and we're going to see that we have 32 possible SR-IOV VFs right there, just like we had in the beginning of the demo where I showed, hey, here's the LSPCI on this particular node. So all this stuff is being tracked for you. All you have to do is request it, and it does all the difficult work for you. So now I'm going to console into one of these SR-IOV VMs, run an IPA, and we're going to see now we have the loopback, of course. We have our ETH0 connected to our default network, one of those flannel type IP addresses. But in addition to that, we now have an ETH1. And this ETH1, I've put in a more distinctive IP range. It's right here at 100.3. And I'm going to go ahead and I'm just going to console into the second instance, and we'll see that there's also an ETH1 here with an IP address in same range. Now that we've got all of those running, what I'm going to do is I'm going to go into one of those. I'm going to use asterisk to create a VoIP call, and I'm going to originate a call from one machine to the next. And here we've got a ton of debug output from it. But what we can see here is that we have sent an invite to the called party, and it contains an SDP, that's our media description. And we have received a response to answer that call from the called party. And they begin the call, and then we see the media coming back and forth between these two machines to actually complete the call. So we have created a data plane, and we have originated some VoIP traffic over that. So that is the demo here. And lastly, you can go ahead and run through this entire demo on your own. Go to dougbtv.com or follow this QR code, and I've got the step-by-step instructions to be able to do that. You don't have to be a super Kubernetes expert in order to do it. You don't have to be a super networking expert to do it. It's fairly simple, and thanks to the hard work of the Kubevirt guys with the operator, this stuff is pretty easy to get going. For me, the hardest part was like getting all the BIOS settings for SR-IOV going. And once I got that, the rest came along pretty easily. So thank you guys. I'll open the floor for questions. We have 3 minutes, I believe.
Thank you. Quick question. How do you define the service attached to a specific SR-IOV? Example, I want one VF goes to just VLAN 10, and second one, I want a trunk. I mean, how would I select in the port which VF I'll get?
So for service discovery, so let me just make sure to clarify it. When I think of services, and I might be thinking of this from a network plumbing working group perspective, is something that we have been exploring, and I certainly would invite anyone to join us with the network plumbing working group, is the interfaces that we create that are additional to your default network are sort of sidecar networks. So they are, what we're looking at doing is making those interfaces complete parallel equals to the interfaces that are available. Part of that is creating service objects in Kubernetes?
No.
That's not? Okay.
No. I wasn't referring to the services in the Kubernetes. It's the service you associate with your VF, I mean network service. Again, VLAN 10, trunk. Pod wants to connect to trunk. How pod can inform whatever driver or something to give me trunk instead of VLAN 10.
Gotcha. So it's about, all right, so you've got a number of cables coming into this box, and you're going, hey, how do I get the particular, this workload needs to use this cable, basically, right? Abdul, do you have any ideas on that particular one?
For that, we need some external. Configuration for external networks. I think there is a Metal LB that projects going on. So we need to looking into that. So maybe we may able to use that to discover this external network.
Any more? One. I'll go with the easy one. Sorry.
Yeah, but the question is, what about service discovery and the storage? Does it work exactly the same as when normal pods?
I will. I'll defer to the Kubevirt guys on the storage side of it. But for the services in particular, is one of our goals for this next KubeCon US is to figure out exactly how we're going to handle the service abstraction. And we actually had a discussion with the group here at KubeCon yesterday, and I believe that we have a good path forward. We have some proof of concept code out there that works, quote unquote. We need to further gel the kind of specification for it, and also with some recent advancements in how service objects work in Kube, we think that we have a path forward for that one. I believe, though, that with storage that you should just be able to mount volumes into the pods like you do any other workload in Kubernetes. So you can make your dynamic volume attachments and whatnot. So you can use whatever storage engine you like.
We're pretty much at time. Is it really quick? Or you think so? Okay.
So my question is, do you have any measurements of performance? Is there any benefit of using SR-IOV without DPDK compared to Mac VLAN, for example?
He says, is it faster?
Is it faster than Mac VLAN is the question.
Because you're removing one layer, you're getting direct bare metal access for your network IOs, and we are using this for a lot of the DPDK application to do even faster network performance. Without DPDK, it also improves your network performance as well. The ordinary kernel networking, yes. Because SR-IOV, a lot of the SR-IOV NIC has its built-in switch in there, so you get this switching capabilities as well.
Okay. Yeah, thank you. Doug and Abdul.